Thank you again for joining us for this webinar on the art of rock physics in carbonate reservoirs, unveiling the impact of accurate results. My name is Monica Iglesias, and I will be giving you a quick introduction to today's webinar. A bit about GeoSoftware. We are a market-leading subsurface geoscience technology provider, delivering innovative subsurface characterization and visualization software and services to the global energy industry. We help our customers integrate and interpret complex subsurface data sets, ensuring robust investment and operational decisions that deliver clean, efficient, and safe operations. The presenter of today's webinar is Fred Jensen. Fred completed a Bachelor's of Science in Chemistry from Texas A&M and has 44 years of experience in the oil and gas industry. His career has included wireline field engineer, sales engineer, petrophysical consultant, and software development management. Fred has worked on field studies in most of the major basins worldwide and has extensive experience in integrated interpretation techniques. Without further ado, please welcome Fred Jensen.
Good morning or good afternoon, depending on where you're joining from. My name is Fred Jensen, and that experience level just means I'm old, which is a good and bad thing. So today we're going to be talking about doing rock physics in carbonate and take a look at some of the value you get from building an accurate rock physics model of a carbonate reservoir. So we're going to be using the Geopain model for this modeling process. And the first thing we do, and I'm going to go through the way we approach it, is we create a lithology model using statistical mineralogy. So you start with the petrophysics. Once we built our lithology model, and our lithology model will, of course, include a total porosity and effective porosity and volumes of all the relevant minerals and volume of clay. We'll then calculate a sonic porosity based on the lithology results, because sonic velocity is a function of mineralogy. We're going to manually determine the volumes of compliant porosity and stiff porosity. And right now, I'll make a point that compliant porosity is also referred to as reference porosity. So you'll see different, or interstitial porosity. So you'll see different ways of referring to that porosity. In the Geopain paper, they refer to it as reference porosity. So although here it's interparticle porosity, which is also compliant porosity. So just to clarify that. And then we'll build a model and evaluate the results. So here's the Geopain model. You mix your minerals and you build a solid rock model using the Roit-Voice-Hill average. And then you put your porosity in and your combination of moldic, reference, and cracks, micro cracks. And that's one of the things that makes the Geopain model unique. And then if you have any wet clays, you put the clay volumes also in the dry rock, and you add the various pores using the differential effective medium methodology. So first, let's talk a little bit about the geology of the reservoir we're going to be looking at. I always like to start my rock physics by trying to understand the geology. And this is from a paper presented by Jeff Reckworth, John Morse, and Mark Brandon quite a while ago in the year 2000. And what we're looking at here is a large carbonate shelf in Mississippi. and we had some stage one, the end of Smackover time, we had a small structural relief, which I think is controlled by Paleozoics, and a little bit of initial salt movement. We had this, they say oolitic, but I'll argue since most of the spherical grains look like they're aragonite, it may also be caused by biological processes, brine shrimp, for example. So we have this little oolitic reef or aragonite reef or shoal or whatever. And then we start deforming it and depositing Haynesville through here. And we start uplifting. And this is an important time period because this exposed porous interval gets exposed by subaerial exposure. And here's where you can have your a lot of the early diagenesis taking place, the leaching and stuff like that. And also you'll start to see some fluid migration through here with the heavy fluids from the Haynesville migrating through. And we start converting some of the some of the limestone to dolomite and possibly the aragonite to dolomite. And the final stage is you build this large structure. This is the interior Mississippi Salt Basin. There's quite a few of these kind of prospects on there in fields that have been developed. You have the up-thrown side and the down-thrown side. The up-thrown is occasionally has a smack over juxtaposed to the Cotton Valley sandstone, so you don't have a trap, so that's one of the risks. On the down-thrown side, you don't have that risk. And so this is an up-thrown side prospect, and it was juxtaposed against anhydrite, so they were okay. So let's look at some of the cores, because there's always information we gather from the cores. And here's the reason I said it might be due to biological processes as opposed to oolitic shoaling, is you'll see that we have some what appears to be aragonite pelletoids in here. And the aragonite has undergone rim microdization, so this is converting from aragonite to limestone. And you can also see a little dolomite crystal at the middle, and that's just fascinating to me. You also see evidence of leaching. This is a dolomite with some limestone cement. You see your sucrosic dolomite crystals beautifully defined there. And then this is a very cemented, mostly limestone. Here you see obvious moldic porosity, and here's a dolomite crystal, and that's probably a coral stem. So it's very complex lithology, and it's changing continuously. These are only 10 feet apart, and this is another 6 feet. So it's constantly changing lithologies. Yeah, having the core information is valuable. So we go ahead and we generate a lithological model of the reservoir. And we do this using StatMin from PowerLog. And we're going to build our model, including lime, dolomite, clay, bulk volume water, bulk volume hydrocarbons, bulk volume bound. We don't have any anhydrite within the limestone section. We do have anhydrite in the Haynesville section up above, quite a bit of anhydrite. So you can see we have a lot of dolomite, a lot of limestone, and some sandstone, and very little clay throughout the reservoir. So this is the model we're going to work with. Of particular interest to me, though, as a petrophysicist, is this invasion profile. The brown is the shallow, and the red is the deep. So this is what's called a reverse invasion profile, and it's caused by displacing borehole in a fluid in the near borehole region, and the fluid being displaced is higher resistivity than the displacing fluid. So mud filtrate, and this is a freshwater mud, is pushing back the oil. And so this is our shallow is reading the lowest, and our deep is reading the highest. Now, that'll be of interest later. A little bit about stiff and compliant pores. And this is a kind of sophisticated way of referring to it. And I thank Jeff Baldwin, a consultant who owns Global Rockscope. But basically, in stiff pores, you have low energy dissipation. So it doesn't impact the P velocity very much. Whereas in compliant pores, you do get a significant impact on the P velocity. And that's the big difference seismically between the stiff pores and the compliant pores. The way I used to think about it was the sine wave just goes around the vugs and it has to go through the compliant pores, but I'm not sure that's 100% correct. I think this is a more scientific way of looking at it. And then we also add in crack pores. So we have our stiff pores, our compliant pores, or our reference porosity, and our crack pores. Now, the crack pores are interesting in that they do not affect the P velocity. I mean, they do not affect the porosity significantly, but they have a major impact on the P velocity. Very disproportionate to the amount of porosity they contribute to the rock. So those are the three types of porosity we're going to be modeling. So let's go ahead and start this process. Our total porosity we're going to generate from our Statmin model, and it's going to be based on the lithology interpretation, and that's our green curve here. Our brown curve is the acoustic porosity, or the sonic porosity. And in this case, I said I'm not going to let the sonic go higher than the total porosity, so I truncated it against the total porosity. And this is your volume of vulgular porosity. So you can see you have a significant volume of vulgular porosity. Now, in order to calculate the acoustic porosity correctly, you need to have the volumes of lithology, and so you calculate a delta T matrix, and then we use the Wiley time average equation to calculate the acoustic porosity, which we'll call the compliant porosity or reference porosity. Now, crack porosity. How do we get a handle on the volumes of crack porosity? Well, if you look at the paper, the Jupain paper, they show here that the stiff porosity, your porosity is actually rather high in reference to your velocity. Your velocity is high in reference to your porosity. So you have a higher P velocity than you would predict. And if you have on your reference porosity, if it was all compliant porosity, they would be the same. This is exactly the same. In other words, your acoustic porosity would be the same as your total porosity. Oh, so hold on, I always forget to do this laser pointer. So here is where your acoustic porosity is the same. Here's where your acoustic porosity is lower. And if you have crack porosity, your acoustic porosity will actually be higher than your total porosity, which sounds strange. But let's take a look at a cross plot. And this is a cross plot of P velocity versus total porosity. So if the purple is your reference porosity, or the HRG is your reference, whichever you prefer, you can see that we have a lot of porosity above the reference porosity. But we do have some porosity below, and this is what we're going to identify as crack porosity. And we have a little bit here, but that's in a very low porosity region. I don't think that's overly significant on its impact in P velocity, but we shall see. So we go ahead and look for it, and here you can see very clearly where I don't truncate the sonic, that the acoustic porosity is higher than the total porosity. And that's your blue polygon here. You can see it highlighted here. So now we know, and you can see the effect on the model velocity. If you do not account for your crack porosity, your model is going to be an error wherever you have crack porosity. So we've got to account for the crack porosity somehow. So what we did is I did this empirically. I don't know any way to do it theoretically, so let's do it empirically. The way the Jupain model works is your crack porosity is subtracted from your reference porosity. So I write an equation, and then to subtract this crack porosity from your reference porosity. And that way we compute the volume of crack porosity, because that's the way the program does it, is that you convert the porosities to a percent, and if it's 80% reference porosity, 15% stiff porosity, then 5% of that ends up going to crack porosity. So that's how we calculate the volumes of crack porosity. When we do that, you can see that now this area where we were not predicting the velocity correctly, we are predicting the velocity correctly. And this is the volumes of porosity. So the blue, once again, is scheduled for it's scaled from 0 to 100%, 0 to 1, 0 to 1, and crack is 0 to 0.2. So you see a little bit of crack porosity here, a little bit of crack porosity here, and a significant amount of crack porosity in this area here, where the acoustic porosity is higher than the total porosity. And then here is your stiff porosity in blue and your reference porosity. I mean, your reference porosity in blue, your stiff porosity in blue, and your reference porosity in brown. And just one more quick look at the porosity volumes. So here's your stiff porosity region, your crack porosity region, and here's your reference porosity. And you can see that we have a significant volume of stiff porosity. So now we've done our petrophysical work and we're ready to go into the rock physics modeling. And now let's look at a Jupain rock physics model. This is the one that's included in RPM. I think we actually now include this model as part of the distribution. Now, it looks complicated, and people tell me this all the time. And at first, I was intimidated. But after about a week of working with it, I understood exactly what's going on. And it's really quite simple. These are your input curves. Each of these boxes is a curve: pressure, temperature, salinity, specific gravity, and so on. Here's where you calculate your raw oil from the API. Here's where you do your brine, oil, and gas properties. These are, again, input curves. And then here's where you do your hydrocarbon and fluid properties. We're going to be using a Woods hydrocarbon. And then we're also going to use a Breeze formula because we think we're going to have patchy water saturation under certain circumstances. And then here's your pore volumes. Here's your total porosity, your reference porosity, your stiff porosity, and I put the crack porosity in here, even though it's not really an input, but it's just, I put it there so I could have an output curve. Here's your mineral fractions from Statmin. Here's your grain mixing, your Voigt-Royce-Hill grain mixing, if you remember back to the Jupain model. Here's your clay parameters. We don't have a lot of clay in the Smackover, but in other parts of the wellbore, you do have a lot of clay, so you want to be sure to model that properly. And then here's the actual Jupain model itself. And then these are just derivative curves from the model curves. These are the 3 model curves. So that's the Jupain model in its entirety. It's a very simple and direct model and very easy to use and easy to modify. The water saturation is one curve which we will modify during the course of the presentation. So we input all of our curves and we run the model, and if we have difficulties, we may go adjust our petrophysical interpretation. But in this case, it didn't take a lot of adjusting of our petrophysics. So here's our model curves. The brown curve is our modeled compressional acoustic, and our green curve is our modeled shear acoustic, and the blue curve is the measured. And you can see we get very good agreement throughout the whole thing. We've even accounted for the areas with crack porosity, so we're really pleased with the quality of the P-velocity modeling. But if we look at it, our bulk density is not exactly right. It looks like it's measuring way too low a bulk density. And I suspected right off the bat that's probably due to invasion, because this is calculated assuming a water saturation, very low water saturation, like 10% or so. That's not uncommon in these deep, hot carbonates. So we went in and we put in our rock physics model. I changed the water saturation from the one generated from Statmin, and I put in an 80% water, which would assume an irreducible water saturation of 20%. Say the density is measuring the invaded zone only, and shazam, we get an absolutely perfect density model now. And our acoustic model isn't quite as solid, but it's still good. So it did have a small impact on the P-velocity modeling, but it really fixed. So now we understand a little bit about the reservoir. We have an idea what the irreducible water saturation might be. So the next step after we do this is we want to not only generate a model, which we've done now and we can use for inversion and for building rock physics models. I mean, that we can input into JSON or Hampson Russell or some other software. We also want to look at the impact of changing some of our parameters on our rock physics templates. And we display those in cross plots. We're iterating on water saturation and total porosity. But we can manually set our reference porosity, our stiff porosity, or our crack porosity, and I probably should have done some modeling. We can vary our lithology and see what impact that has on our seismic. And so we can vary our volumes of lime, sand, and dolomite. And here's our first model, and you can see this doesn't encompass a lot of the data in terms of the VPVS, so we're seeing a significant impact here. It does encompass a lot of the model curves here. So, and this is 70 lime, 30 dolomite, and a 50-50 split. If we stick with the 50-50 and go 90% lime, now we're almost completely off. Where it is being fairly accurate is up here, and that says a very low porosity rock is almost all limestone. So that's a significant observation. And once again, the p-velocity versus density, it doesn't really change a lot on that spectrum. It's the VPVS where you see the significant impact. Now here we change it to 10% lime and 90% dolomite, and now we're modeling a totally different part here, and now you can actually see some difference in here. That now we're covering a different part of the p-velocity versus ρb data set. And here we're encompassing a whole lot of the data. And then, of course, if you keep varying them, you can eventually model all of the different parts and figure out what is causing the sonic response that you're observing. Now, one other thing I was interested in is what is the Brie exponent going to do? Trying to get an understanding of what patchy water saturation does. So here we're varying the Brie exponent from 2, which is virtually no impact, to 20. And when we do that and we leave the water saturation, it's about 0.08, which is an average over the Smackover with very low water saturations in this high temperature, high pressure dolomite, dolomitic limestone. But if we're at 80% water saturation, we see a huge impact on the velocity as a function of the Brie exponent. And I'm wondering if somehow we could figure a way to use that information where you could model the transition zone if you had a water oil contact where you could see that and image that seismically. And that's one of the values of building a good rock physics model and then looking at the templates as you begin to see what's going to be impacting your seismic data. So I'm going to make some observations and then I'm going to go a little bit further. So this isn't really the ending yet. The petrophysical interpretation is critical. And it is an iterative process. I did change the interpretation to get a better rock physics model. I had a lot higher volumes of clay initially. It just didn't seem to work. So I lowered the clays and the models got significantly better. And PowerLog RPM, you do a detailed construction. I know it looks like it would be kind of complicated. It's actually fairly straightforward, but it'll give you control over every aspect of the model. And the templates are an effective way to visualize and understand the effect of the parameters on the elastic properties of the reservoir. And I like the Jupain model for complex and involular carbonate formations. It seems to work quite well. Now, if you're going, you have an option though in the Jupain model in PowerLog. You don't have to do it petrophysically. You don't have to determine the volumes of rock. You can say, I'm going to use the pore type fractioning model options within PowerLog. This is what you get when you double click on one of the nodes on the RPM model. So I could do pore fraction modeling and I could model my crack volume and I'm going to input my P velocity and this is my measured P velocity and my total porosity. And I'm also going to input all the other parameters variable. And this I can go in here and I can model my crack volumes, my stiff volumes, and my reference volumes. And when I do that, I get a very accurate model across the reservoir. It's probably a little higher quality than I got when I did it petrophysically. It doesn't do as well outside, and that's because of the problems with data quality. Whereas petrophysically, I can account for that and so get my model continuously. Within the Joupane model, this determination of reference total and crack porosity causes some issues. There's a way around that. I could have done these in intervals and solved that problem, but I was just doing this. But you can see what's interesting to me about this is that the program calculates the volumes of stiff porosity, reference porosity, and crack porosity. And you can see here where I see lots of crack porosity, they see lots of crack porosity. So it's interesting that the software ends up on its own computing parameters very close to what we computed doing the modeling. So you have the two ways of using the Joupane model. You can do it all petrophysically, or you probably still need the lithologies, even if you're going to let the Joupane model determine the volumes of crack, reference, and stiff porosity.